Hi, I'm Will from Tested.
Norm from Tested.
Norm, 3D printing.
3D printers.
3D printing with 3D printers.
It's a real deal. We were early on 3D printers with the first MakerBot.
Yeah.
And since then, we've used pretty much all the MakerBots.
Except for the very latest, most recent experimental Replicator 2. Yeah, I spent a lot of time printing stuff over the last 3 years.
And there may be a lot of misconceptions of how easy 3D printing is or how difficult it is. And we just want to explain the whole 3D printing process and give people an understanding of what that entails.
Kind of a brain dump both about the basics of 3D printing and then specifically like what you get when you spend $2,200 on a Replicator 2.
So watch this video if you've never done any 3D printing before, and even if you've done some 3D printing and maybe you've shared some of our experiences. And you can learn something and give us feedback.
So the first thing we should talk about is what actually 3D printing is. It's a really simple process. Basically, you have a couple components that work together. The main one is this thing called an extruder, and all it is a motor with a gear that takes plastic in the top, heats it up to the melting point, and then spits it out the bottom, usually in a very controlled manner. So you use what's called a stepper motor, so you can control the speed at which the plastic moves through. And then there's another thing called a carriage. The carriage is very similar to a normal paper printer in that it moves that print head, the extruder head, back and forth across a two-dimensional surface. The only thing that really changes between this and, say, a printer that uses paper is that this also has a z-axis. So it can lift up and lift up and lift up. So it can apply a layer of plastic, lift up a tiny amount. That amount is typically the vertical resolution of the printer. Put another layer of plastic down, raise up, put another layer of plastic down, raise up, and so on and so forth.
So there are many analogs to a traditional regular paper printer or laser printer.
It's a lot of the same technology, except for a normal 2D printer is a one-dimensional printer, basically, and you spool the
in X or Y, where the print head is moving maybe across one axis and the paper is moving across another axis.
Exactly.
Here, the print head, at least modern 3D printers, move both in X, Y, and then the Z is where the surface moves.
The Z is the equivalent of the paper in this case, because the Z only moves one way. You start at the bottom and work your way up, or in some cases you start at the top and work your way down.
So right now, with modern 3D printers, we can print plastic.
Yeah, so there's a bunch of different materials that you can print. The most common are ABS plastic and PLA plastic. ABS is a normal, actually the blue stuff over there is ABS. The melting point of both of these is around 200 degrees Celsius, so double the boiling temperature of water. And they have different properties. ABS is a little bit more difficult to use. It cools slower, which means that it has a tendency to shrink as it cools, and that causes an effect that we call warping, where basically the edges of a print will kind of curl up if you do something big or if you don't have the platform heated. That's why the Replicator 1 over there, the wooden printer, has a plexiglass case around it. That helps insulate it from, like, a cool breeze from the air conditioner can have a negative impact on your print when you're dealing with ABS. It's also a little bit more toxic. It produces fumes. The material sheet on it says that that's perfectly safe to breathe the fumes. I find that when I do a lot of ABS printing, I get a little bit of a headache at the end of the day, which probably means it's not real good for you.
So to recap, the major components of a modern 3D printer is the print head with the stepper motor, and then the carriage.
That's the thing that holds the print head.
Holds it and moves in different axes.
Although sometimes the platform, the thing that you're printing onto, moves underneath the print head. Right. So it's like there's a bunch of different ways to do it.
A carriage, a build platform, which is that surface, and that kind of determines, combined with the carriage, the size of the object you can build. And in terms of the MakerBot 1, that is a heated build platform. Yeah,
so the reason you use a heated build platform is either for adhesion, to get the material to actually stick to the platform, or to help reduce warping. So, I mean, there's two different ways. The Replicator 2, the base Replicator 2 has, I think it's like a plexiglass or polycarb or something, acrylic. Build platform. It's not heated. The Replicator 1 has a heated build platform. The experimental Replicator 2 has a heated build platform. And that also adds a lot to the energy that's used. Right. The heated build platform has a pretty heavy thermal capacity, so it takes a while to warm up. and it takes a fair amount more energy to run.
And really, and then we talk about the materials, ABS plastic and PLA, which...
PLA is the other, this is the big enhancement. It's a corn-based plastic. It comes in a variety of different colors. And the benefit of it is it cools much more quickly than ABS, so warping is less of a problem. It also comes in some interesting colors, like that translucent blue I think is really pretty, and you know, it diffuses light in an interesting way for things that you want to be able to shine light through. Right. The other benefit of PLA is it's corn-based, so it's non-toxic.
And then with both types of plastic or any material right now, within the stepper motor that is heated and melted, from spools, so the material you buy in spools.
Yeah, so the extruder is really, really simple. It is literally a hot end, a thing that gets to 200 degrees Celsius, a motor with a gear on it that grips into the edge of a piece of spindle plastic and pushes it down, forces it down to that hot area. So what that does is reduces the amount of plastic that comes out at any given time from like a 1.75 millimeter, which is the diameter of the plastic going in, to 0.4 of a millimeter.
And that determines the quote-unquote resolution of your print.
That plus the vertical resolution of the z-axis. How far up and down
the build platform moves per each row of printing.
So the theoretical maximum resolution, and this is a smaller is better situation, for both of these printers is 100 microns or 1/10 of a millimeter. So it's a very, very thin resolution. It's about the thickness of a fairly thick sheet of paper. And you can see the difference here. This is a difference in quality really good. This is, as you can see, it's an R2D2 head. The one on the left is a 0.27 millimeter resolution, which is the medium setting for the Replicator 2. We'll talk about that stuff in a minute.
And for this type of build, you can actually see all the lines very clearly.
Absolutely. It's a rough sketch. Is the analog I would use.
And then when you get something much finer, the finest that the Replicator 2 can do today,
or the Replicator 1,
or the Replicator 1, then it's much smoother, but you can still see the lines.
Yeah. So before we move on from the plastic, you can use PLA in the Replicator 1, or you can use ABS. As long as you have a heated build platform, you can use ABS relatively easily. It's difficult to use ABS on a non-heated build platform, especially to print large stuff. So that's the big difference. That's why the Replicator 2 is a PLA-only machine, and the Replicator 1 you can put wherever you want.
And in terms of temperatures, 220 degrees?
220 for ABS. PLA melts anywhere from 180 to 210. It starts to scorch if you get it much above 230.
And then the build platform, if you're using a heated build platform, how hot does that have to heat up to?
It depends on the plastic again. So for ABS, you usually run at 100 or 120 degrees Celsius. For PLA, some people recommend running at room temperature. I find if you run it at 60 degrees, then it makes it very easy to break the model loose when it's done. So that's important.
Okay, so that pretty much covers the hardware side of a MakerBot.
And I mean, there's electronics and stuff like that that makes all the
controllers
stuff run. There is a controller inside, which has an SD card reader. And basically, the way these machines work is you take a 3D model, typically an STL file or an OBJ file, or you can use most 3D CAD packages to render out one of those two formats.
And these are standard formats.
Fairly standard formats.
The STL file, whether it's on a MakerBot or some other 3D printer, you start with an STL file.
Exactly. So that is a 3D model. It's not sliced. So once you have the 3D model, and you can also so you can create them yourselves using a program like SketchUp or AutoCAD or 3D Studio Max, or even free stuff like 123D Design or 123 Capture and all that stuff.
Once you have an STL file, you said not sliced. Now the word slicing is important because in terms of a 3D model, it's a 3D model printed and sliced in many layers.
Yeah, so once you have the model, you ingest it into a program called, well, I call them slicers. I don't know what the technical term is. There's a handful. MakerBot provides Makerware, which is their own closed source internal tool. It's very easy to use. It's relatively fast at the medium settings. It gets very slow at the highest quality settings. And there's not a whole lot of knobs and dials to turn. Because when you're dealing with this slicing process, let me explain what the slicing process is. What the slicing process does is says, okay, you have a model that you want to be 400 millimeters high, and you want the vertical resolution to be 1/10 of a millimeter. So that means you're going to need 4,000 layers, if my math is right.
Yep.
And each layer has a toolpath that's defined. So on each layer, the slicer says, okay, the printer is going to start here, and then there's going to be a two-dimensional line, or maybe a series of two-dimensional lines that move on that stick to the layer below, and will provide the base for the layer above. And it literally defines. It says, okay, start at this coordinate, go here, then go here, then go here, then go here, then go here. Sometimes millions of times on a big complex print.
And it's smart enough to know that when you're building a volumetric object, the layers obviously are not solid for every layer.
You can make it solid. That's a little tricky.
Then you're using a lot of plastic.
And it'll take a long time.
And it'll take a long time. But what you want to do is use the algorithms to be smart enough so that it's solid where it matters, and then it builds enough of a structure inside so that when you add those layers up, it is a solid object.
If you built your model properly, then it should the software, the slicer should know what should be filled and what should be hollow. So for example, this guy, the lamp, show the lamp. Or actually, show the White House first. That's good.
Yeah.
So this is what the inside of a model looks like. This one it broke loose mid-print and it skipped. But if you pull off that top layer of cruft there, and it's just a grid. There's a bunch of different grid patterns it can use. MakerWare has some that it uses by default. Typically, it's hexagonal or square, sometimes triangles. And what this does is, as the plastic's coming out, if it doesn't cool fast enough, if it doesn't have something to rest on while it's cooling, then it'll kind of sag and make something that looks like a little bit like droopy spaghetti. It's kind of sad. So this internal structure is a function of the software.
Right, and it's mostly the same between the layers, but you can tell that it's denser on the edges because it knows that's where it's supposed to be solid.
Yeah, so there are several variables when you're doing the slicing that are really important. Infill percentage, which is what that is, that's probably about a 5 or 3% infill, and that's just the total amount of interior volume that's filled. The number of shells is the number of outside layers, so the space between the inside of the model and the outside of the model, and changing that can affect both the kind of fine detail on the model as well as the thickness and like how sturdy the overall model is.
Okay, so you have an STL file.
Yeah.
You run it through a slicer.
Yeah.
And these are free tools that you can download.
Some are free, some are paid for. There's MakerWare is MakerBots' own. It's very simple and easy to use, but not particularly powerful. SkyneForge is the open source version. It came with previous MakerBots. It is very powerful, very difficult to use. And then there's other things like Slicer, which is SLIC3R, and there's a couple of others.
Which one do you recommend?
Software. If you're just starting out, then MakerWare is great. It's an easy way to learn. You're not going to get really good, high-quality prints out of it, I find. We can talk about that in a little bit, but it's great at the 0.27 millimeter resolution. It's very fast. They use their own custom proprietary slicer code that is much faster than the SkyneForge default. When you go up to the 0.1 millimeter, 100 micron resolution, then it gets very slow, and it actually uses SkyneForge.
And when you're saying very slow, you mean the actual computing and running the program.
So generating those tool paths and figuring out how many layers there are and what the layers look like as it's printing is a really complex problem, especially for a big, complex model.
Right.
It can take, for example, that R2-D2 head, I think for Miracle Grew, the MakerWare specific one, took maybe 5 minutes to run. For the 0.1 micron resolution, took like 2 hours. So it is a big, big, big jump in time, sometimes even a couple of orders of magnitude.
Right.
You get better control and better results. Unfortunately, Miracle Grew can't do 0.1 millimeter resolution right now, or it doesn't do it very well in my experience.
And so when someone like Chris Anderson says, you go to Thingiverse, you download dollhouse furniture for your kids, it's not like you press download and then send to printer. You press download, there's a little tweaking, and then you have to slice it, and then you put on an SD card and then put it in the MakerBot. So
yeah, the thing that happens is you develop a feel over time for what the different settings are. You can kind of, once you've gotten used to it, for example, if you take those chairs out, we have 3 of the wingback chairs, and I don't have the legs on a couple of them. But if you look at the seat of the 2 small chairs, one of them isn't filled. There's gaps in the one on the left. There's not gaps in the one on the right. Those horizontal lines on the seat of the chair are actually holes because I didn't have enough shells on that particular model when I was printing it.
And this is just configured in the slicer software?
You configure it in the slicer software generally. Like I said, the difference between SkyneForge and, say, MakerWare is that SkyneForge has literally a couple hundred options, and MakerWare has maybe a half dozen.
But then when you take a 3D object and you download it, you can also do something to scale it.
Yeah,
you can configure that too.
So yeah, the different software has different options. MakerWare is probably the gold standard in this. It lets you scale to a specific percentage, so you can maintain the scale that you want, or you can just kind of eyeball it or make it as big as the machine will print, or whatever you want. You can also place multiple things on the build platform. So this is a long process. Printing something like that chair or like this lamp in front of us. Literally, that lamp took 8 hours to run, the two pieces. So I was able to put both pieces on the print platform at the same time, and they were able to go in a, then I could leave the machine and it would print unsupervised, basically. The R2D2 head at fine resolution took a very long time because I had to run it at a very slow speed.
Okay, so you've practice a lot with the slicer, depending on which one you've used, and then you put it on an SD card and you put it in a MakerBot or some other 3D printer.
What the slicer spits out is a text file or a binary file that contains GCode. GCode is a kind of a universal descriptor for CAD/CAM machines like this. So it basically says, here's the start point, here's the end point, here's what you do at every step in between, move the x-axis this far, the y-axis this far, go at this rate, all that kind of stuff.
GCode applies to most CNC.
Yeah, you use it on the $2,000 MakerBot or on like a $250,000 Tormac CNC mill.
Yeah, and that is the big breakthrough in 3D printing, having GCode. In terms of CNC, like when you think about old printers, and old printers had different protocols.
That is definitely true. Yeah.
Now everything, because it interprets the G-code, that's the standard.
So the way to think about this that's important is the G-code is basically even though it is a common language, there are specifics that are specific to each machine. So when you make a piece of G-code, theoretically, I could run the same G-code on the Replicator 2 and the Replicator 1. It's not going to work very well. Your STL is a universal file. The G-code is specific to each machine because the slicer has to understand the capabilities of the printer in order to make the optimal tool path for that printer. If the resolution of the nozzle at the bottom of the extruder is different on one printer than the other, then that's going to impact what the finished result looks like, and you have to account for that when you're doing the slicing.
So for someone who's casual in 3D printer or just got a 3D printer, where are the ways that 3D printing can break down? And that they're
there's a bunch of ways.
Let's go over because some of them.
Okay, so the basic stuff is that the print head can get clogged. If you leave it hot for too long, especially with PLA, the plastic breaks down, and you end up with a big goopy blob of plastic coming down out of the printer. That's gnarly. Right. Other stuff is like the print bed on the Replicator 2, at least the one we have that's a loaner from Adam.
The platform.
The platform is wobbly. And when you're talking about a tenth of the thickness of a piece of paper, having a wobbly print platform, it's not acceptable. It's not good.
Calibration is needed. It makes almost regular maintenance.
It's regular calibration. Yeah. On the older model printers, like the Replicator 1, which has a bolted down to the bed print platform, it's much more stable.
You set it once, and maybe you tweak it a couple times.
You may adjust it for specific things.
Right. But it's not like week to week where.
Every 3 or 4 prints. Every time. The other stuff is things like the adhesion to the surface is a continual challenge. So getting the plastic to stick, that first layer of plastic to stick to the model well enough that it doesn't break loose during the print, but does break loose when you're done printing is a kind of fine balance. On the Replicator 2, I use blue painter's tape, which is what they recommend. A lot of this stuff is in the documentation. Some of it's not particularly well documented, but you have to wipe off the blue painter's tape with rubbing alcohol or acetone to get the finger oil off, because the oil from your fingers from touching the platform is enough to make the plastic not stick very well over a 6 or 7 hour print.
And then they can warp on the bottom and just shrink differently.
So a lot of these problems are interrelated. For example, if your build plate isn't level or it's too close to the print surface, then there won't be enough room for the plastic to squeeze out, and that'll cause the filament to strip, and then plastic will stop coming out, and you end up in a situation where something stopped working. It's the same exact symptoms, but there's 15 different causes for it potentially, and it's really hard to troubleshoot, especially if you don't have experience with it.
It's a very time-consuming process.
It's very time-consuming. The price of failure is really, really high.
Yeah, you could spend a couple hours
Slicing. Yeah.
And well, you don't know it's going to work.
Yeah.
And then you got to print, and that could be a point of failure.
Yeah, I mean, the printing is most likely where you're going to determine the failure.
Right. And that could take 10 hours.
Yeah, so if you're looking at something that takes a couple hours to slice each time you want to try it, and then another 7 to 10 hours to print, then you get maybe 6, 7, 8 chances at that a week, even if you leave it running overnight.
Right.
And it may get 90% of the way done, and then bomb out in the last 3%, which is what happened with the lamp. If you look at this, the top is very clearly not finished. Flip it down, and what happened was it broke loose from the tape. It warped a little bit on the bottom, pulled off of the build platform, and we ended up with the plastic pubes that you have over to your left.
Yeah, it
just went crazy because I left it running overnight. You can iterate very quickly with small, simple stuff, but you can't iterate very quickly with big, complex things. And the place that it breaks down is printing large stuff. If you're printing things like
physically
the chairs,
large, not complex, but physically large.
Yeah, so if you look at the ABS, the game pieces and the chair and stuff like that, that all looks great. If you're looking at things like the Tetris pieces, which I use to prototype my shelves, then they're very simple and were very fast to print, but it was incredibly useful because I was able to see what I wanted the shelves to look like in the end before going in there.
But if you're doing something that's complex,
things,
that has mechanics,
pre-assembled gear systems and stuff like that, I spent hours trying to get this to print. This was the result of about 2.5 days worth of work all told, and it works. It's amazing. That was printed all in one piece, and it is by far the coolest thing we've done. It's a Planetary gear system. It spins up at full speed. It's high friction, but it's a round bearing that works, and you can 3D print it. I think that's really cool. On the other side, I printed things like watch bands that were highly questionable and didn't work very well at all. And then I've also printed things like the bottom of the lamp that was completely failed. So you have to be ready to experiment. You have to have a lot of time. If you don't have a lot of time, then maybe 3D printing at this stage probably isn't.
It's an investment not only in the initial investment, because a MakerBot can cost $2,200 just for one print head.
Well, so there's many cheaper options available.
As cheap as $500, $500 to $600.
Yeah.
But then you're spending even more time, like we did with the second generation MakerBots, in terms of troubleshooting.
The guys at Make did a 3D printer special last year and tested a whole bunch of different printers. And I know that there are some good options in that $500 to $1,000 range. The thing that's changed is that the software is much better now than it was 3 years ago when we started. So there has been, I don't want to sound like we're down on 3D printing. It is much easier to get into 3D printing today than it was 3 years ago.
Yeah.
It's both cheaper and the software is better. Even the complex software like Replicator G is much easier to use now than it was before.
You're not building your own extruder and stepper motor.
Exactly.
Taking a day or a week to do that.
When we built the first cupcake, we got essentially a flat packed 3D printer and had to assemble everything from the chassis to the extruder head to the build platform.
You can still
motors,
do that
electronics, all that stuff. Oh, absolutely.
If you want.
And if you're buying a $400 printer, that's what you're going to do.
Yes. But you can also spend 4 times as much and get something that will come out of the box and you just calibrate.
Well, I think that's a little unfair though. I mean, I think the promise of out of the box, easy to print is kind of true with the Replicator 2. In reality, though, I don't think it's a fair thing to say, and it sets an expectation that people shouldn't have when they're getting this. This is still something you're going to spend some time on.
It's not an HP printer.
Yeah, it is not. Take it out, load it up, put the ink cartridges in.
And that's something that 3D Systems wants to be.
I think
locked-in cartridges and ways to cut off the cruft. Yeah.
I mean that stuff. So the difference here is that you can take the SD card that they provide, jam it into the machine, and print the sample stuff, and it'll probably turn out okay if you lucked out and did a decent job leveling the build platform, and your tape is on level, and there's no overlap between the different sections of tape, and there's no bubbles or anything like that. You're not going to be able to do that at the highest resolution. They advertise that the default for printing is 1/10 of a millimeter, and that's nonsense. I mean, it takes literally a couple of orders of magnitude more time to slice an object at 0.1 millimeters than it does at 0.27, which is the medium default, and is actually the default of the software that they ship. The quality is commensurate with that. I mean, it is twice the resolution at 0.1 microns. It takes twice as long to print or more, and it looks a lot better. But you're not realistically printing stuff at 0.1 microns. That is an advanced move for advanced users. And it's very slow.
Still it's a hobbyist business right now?
I think it's for people who, if you need a 3D printer, you probably know it. Like if you are, I think there's a couple of really good use cases. I think Chris Anderson's print your dollhouse toys use case is great.
But he probably don't buy it for that.
I think if your kid is really into that stuff and you can get a $400 or $500 printer, the difference between the cheap printers and the expensive printers is support and the size of the print area.
Support
the resolution
from the company.
Support from the company. The size of the print area is if you're printing dollhouse furniture, the $400 machine is great. The resolution is going to be roughly equivalent, depending. You can pay attention to that. The MakerBot is 0.4 millimeters. Some are bigger, but most are about that, and they use the same size filament, so that's not a problem anymore. I think that's a great use case. It's a good way for a kid to learn how to do 3D modeling. This is a great educational tool, because if you're 12 years old, you're really into building stuff in 3D CAD programs, and you're into learning that, this is a gift that keeps on giving, right?
Right, and the software will keep on getting better.
The software has improved dramatically in the last 6 months.
Makerware works with the old replicator,
yes,
and hopefully in future versions will also work with the existing models.
It should. If you want to build this to build machines, it requires a much greater level of precision from the software and from the hardware. Like, you need to really understand how the machine works. You need to really dial it in. You're going to end up spending hundreds and hundreds of hours getting it to the point that you can print something like that orbital gear system. It's a pre-printed mechanical assembly. If you're an architect or something like that, this is an okay thing to use to build your models and stuff like that, rather than cutting them out of foam core. Although you may not get the quality that you want out of this generation of device.
Yeah. So the MakerBot Replicator 2, it's an amazing piece of technology, but
I wouldn't buy it.
You got to really need it and really be willing to spend the time with it and be able to afford it.
I mean, I think if we were looking at $1,000 versus $2,200 or I think $2,800 for the ABS dual head model, it makes much more sense. This is something, if you have a business need for a 3D printer, then you can do it. If you want something to noodle around with at home, buy one of the RepRap kits, buy one of the either Cupcake or Thing-O-Matic variants, and go nuts with that. You'll have a much better experience, and you won't spend as much money.
Awesome. So, well, we'll find more about 3D printing and 3D printers and the MakerBots.
We do 3D printing every week.
Every week on tested.com. Subscribe if you're watching on YouTube. And hopefully you learn a little bit about 3D printing today.
See you guys next time.
Bye.